We're going to do an example here using the limit definition for slope. So given this function, y equals 1 over x, we're going to find the slope of the curve at some point x equals a, as long as a is not equal to 0. So we are dealing with a function that looks like y equals 1 over x. And the only reason we say that, we're going to plug a in and find the slope at that curve, x equals a, the only reason we add this x can't equal 0 is because x equals 0 is not in the domain of the given function. Okay, so we'll see a lot of addendums to problems that remind us that, hey, we can't have 0 in the denominator. So don't let those extra terms confuse you. So our slope definition that we are now using is that m equals the limit as h approaches 0 of f of x sub 0 plus h minus f of x sub 0 all divided by h. So we want to calculate this limit. And ideally, when we're calculating limits, we want to take that 0 and plug it in for my h value. But I can't plug 0 in, obviously, because it would give me an undefined value in the denominator. So we are going to use the fact that x equals a. So we're going to let x sub 0, our x value in this case, that is going to equal a. So what we'll set this up as is we'll say, well, this is going to be equal, my slope is the limit as h approaches 0 of f of a plus h minus f of a all divided by h. And so at this step right here, it really doesn't look all that different from the definition that we're using. But we need to figure out a way to evaluate this. I need to manipulate this. I need to manipulate this rational expression in a way such that I can plug 0 in for h. So one thing I often do, especially when I have h in the denominator, is I'll rewrite that and I'll say, well, this is the limit as h approaches 0. Dividing by h is the same as multiplying by 1 over h. So I've got 1 over h, f of a plus h minus f of a. So what is f of a plus h, right? F of a plus h. Well, that would be me taking a plus h and plugging it into my function for x. So this gives me the limit as h approaches 0 of 1 over h times, that would be 1 over a plus h, minus, and f of a, that would be the same as me taking a and plugging it into my function, so that would give me 1 over a. All right, so at this point, we need to try and add these two rational terms together. And in order to add fractions, we need a common denominator. So I would have the limit as h approaches 0 of 1 over h. This 1 over a plus h, I'm going to take that and multiply by a over a, because I'm multiplying by 1, which is always legal, minus that 1 over a, which I will then multiply by a plus h over a plus h. Simplifying what I have inside my square braces, I have a minus a plus h all over a times a plus h. So I added my numerators together or subtracted them, and then my denominator became a times the quantity a plus h. simplifying in the numerator, this is the limit as h goes to 0 of 1 over h. A minus a cancels, and then that minus right here is going to distribute to this h. So I have minus h over a times a plus h. Now, as we have manipulated what I have in my square braces, you'll notice I have a times h in the numerator and a times h in the denominator. Those terms, h over h, is going to cancel. So this means I am now calculating the limit as h approaches 0 of negative 1 over a times a plus h. And at this point, if I take that 0 value and I plug it in for h, I'm going to have negative 1 over a times a plus 0, which means I end up with negative 1 over a squared. So my slope here, m, is negative 1 over a squared. So for any x value, as long as it's not 0, this expression, negative 1 over a squared, that's going to represent my slope. So this is the slope of my function. Remember, my function was y equals 1 over x at x equals a. So for any a value, as long as it's not 0, that represents my slope. So let's take this another step here. Let's find the slope at, say, x equals negative 1. So again, we are given y equals 1 over x, and the slope for any a that is not 0 is m equals negative 1 over a squared. So if I told you find the slope at x equals negative 1, the slope, we would just say m equals negative 1 over negative 1 squared, which is negative 1 over positive 1. The slope would be negative 1. So I've brought a graphic in from our text, which kind of will help us think about it. So what you see here, this blue curve, this represents my rational function. And what we did in the first part of the example, we said at some a value, we were going to find the slope, right? And that a value could be anywhere. So you'll notice there are lots of points on this line. All right, we've got lots and lots of points on this line. So for any point, if I know what that x value is, I can plug that in, and using my slope formula, I can determine the slope there. And what you'll notice is that all these tangent lines, all of these lines have a different slope, right? Because the slope changes along that curve, because the slope isn't constant. There's no constant rate of change on something that's curved. This isn't linear. And if we extend that to the second part of our example, which we just did, and we say, well, what is the slope at that point where x was equal to negative 1? The slope of that tangent line is negative 1, right? It's a negative slope, down 1, forward 1, down 1, forward 1. So to expand on this same problem, we're still given the same function, y equals 1 over x, and we now know the slope, negative 1 over a squared, and that's for any non-zero a value. The question here is, where does the slope equal negative 1/4? So if we know the slope, at what x value? Where? So we know the slope right? The slope equals negative 1/4. So this would be negative 1/4 equals negative 1 over a squared. Multiplying by a negative on both sides, that's the same as 1 over 4 equals 1 over a squared. Cross multiply, a squared equals 4, and square root both sides, we would get that a equals plus or minus the square root of 4. So for any a value, when a is positive or negative 2. So at x equals positive 2 and at x equals negative 2, the function has a slope or rate of change of negative 1/4. And so let me pull a picture in that will help us think about that as well. So if you look at this graph, this is the graph of our function. And at both points where x is equal to positive 2 and negative 2, if you look at the slope of that tangent line, they both have the exact same slope. The slope is negative 1/4. So there are 2 points on that curve where the slope is equal to negative 1/4. So that concludes our example. Remember, there were 3 parts in this example. We looked to find a general slope. We found the slope at a specific point at x equals 1. And then we said, well, if we know our general slope formula, we could then determine where that slope occurs. So we found x values using the slope.